This meeting is being recorded.
I'll be presenting to you on the topic flattened partitions, where we're interested in pattern avoidance and the behavior of some statistics. You will get to see the details as I go on. And this is the work I'm going to present is joint work with the Muhumuza Ronald. Muhumuza Ronald has been my master's student, so I gave him a project which we could do such that we get results that we can compile together and then get a manuscript which we can submit to a journal for review and then publication. So I would be very happy if I receive comments or any suggestions which you can use to improve this work. Okay, so this is how I'll move. I'll begin with some background or introduction, and under this I'll basically look at the definitions and the preliminary knowledge or work that has been done, which led to the problem that I'll be presenting to you about. And basically, we are going to be looking at these kind of permutations, that is the 1, 2, 3, 4, and 1, 2, 4, 3, avoiding flattened partitions. Then we shall also look at the 1, 3, 2, 4, and 1, 4, 2, 3, avoiding flattened partitions. And I'll finalize with these last three, avoiding flattened partitions. So just some brief introduction. So wherever you see this notation here for any fixed positive integer, that will just be representing a set with elements 1, 2, 3 up to n. And a permutation sigma over n, I think this is a very common object in combinatorics and simply a bijection from this set with n elements to itself. And in this work, we shall be representing that permutation sigma as simply a word using the one-line notation. So we shall just be writing the images for each of the elements from the set n. And if we have a permutation sigma, we shall say that a sigma has an occurrence of a pattern tau if we can find in sigma a subsequence that is order isomorphic to tau. Otherwise, if sigma does not have such an occurrence, then we say that sigma is tau avoiding. I included an example here of a permutation of length 4, and I'm saying that this permutation contains two 2, 3, 1 occurrences. Which ones are they? We have 3, 4, 1. When you try to write this in standard form, when you try to reduce it with the smallest entry taking on 1, the next smallest entry taking on 2, and so on, realize that 3, 4, 1 is actually order isomorphic to 2, 3, 1. And the same applies to 3, 4, 2. 3, 4, 2 is also order isomorphic to 2, 3, 1. And because this permutation consists of subsequences which are order isomorphic 2, 3, 1, then it contains an occurrence of this pattern. And we can also observe that this permutation is 2, 1, 3 avoiding, because within it we cannot find any subsequence that is order isomorphic to 2, 1, 3. So this definition will be very helpful to us as we move on. And then I also have a run in a permutation, and this is simply a maximal increasing subsequence in a permutation sigma. For example, given this permutation sigma 1, 5, 2, 6, 7, 3, 4, this has 3 runs, and those runs are 1, 5, 2, 6, 7. We are only interested in maximal increasing subsequences. Then whenever you come across an element which is smaller than the last element in that subsequence, that's where our run ends. So this permutation here has 3 runs, as shown here. And given a non-empty set, we're defining a set partition P to be a collection of disjoint subsets, which we are denoting as B1, B2 up to Bk, and we shall be referring to them as blocks, such that the union of these disjoint subsets of S gives us the entire set. So as long as you have a set S, find a union of any finite number of disjoint subsets. If that union gives you the set S, then we say that disjoint union of subsets is or forms a set partition of S. So Catalan, in his work that was published in 2009, introduced the operation on a set partition, which he called flattened P. And this flatten is just a command borrowed from Mathematica, because in Mathematica, what it does is that it puts together different lists or sets or subsets, removes their parentheses, and then writes them together just a single list. So Catalan said that with this flattening command, that if you have a set partition P, which you said we shall write in this form, B1, B2, Bk, where these are different blocks, and each block has elements written increasingly. And these blocks are also arranged from left to right in increasing order of their first elements, meaning that the first entry in B1 has to be less than the first entry in B2, and so on up to the last block. So when you remove these marks here, which are separating the different blocks, and then write the resulting word as simply a single word, then the resulting permutation is what we call a flattened partition. Now, in this work, I'm mostly going to focus on these flattened partitions. So in brief, if we decide to define them in terms of runs, we can also define a flattened partition as a permutation where its runs have been ordered from left to right in increasing order of their first entries. So you can also view flattened partitions under this context of the run statistic. And it's also important to note that with this flattening, because we are applying this operation on a set partition, so realize that different set partitions under this command or operation can result into the same flattened partition. So this flattening operation is not injective. And I'm going to let tau to be my pattern of length 3. So there are patterns from this set, 1, 2, 3. So we have 6 elements. And I'll let tau prime to be my patterns of length 4. And I'm looking at this set here. There are 8 of them. There are 24 permutations of length 4, but due to some equivalence classes, we realize that all the 24 permutations can be represented by simply this set consisting of these 8. And they are the ones that I'm going to mostly focus on. And I'll let this S n tau denote the set of set partitions of n whose flattening avoids a pattern tau, and Fn tau denote the set of distinct tau avoiding flattened partitions. So I'm using the term distinct here just to emphasize that the flattening operation is not injective, and so when we look at this set Fn tau, we shall mostly be interested in those distinct flattened partitions. And what Catalan did in his work, he investigated the number of set partitions of n whose flattening avoids a pattern tau. Remember, tau, I said these are patterns of length 3. So all Catalan was doing was looking at any set partition, and then he would apply the flattening command on that set partition. And whatever comes out, which is now a flattened partition, he would now look at the pattern avoidance for each of the patterns in the set tau. So he was actually counting set partitions, because those were the objects he was using. Whatever flattened partition results from a given set partition, then he would get the resulting flattened partition and then looks at the pattern, whether it is there or it is being avoided. And this is what he got. For the pattern 1, 2, 3, he had this counting sequence 1, 2, 1, and then after that the rest of the terms are zeros, so that's a trivial. And then for tau equaling to 1, 3, 2, he ended up with a power of 2. For 2, 1, 3 and 3, 1, 2 patterns, he had this sequence f of 2n minus 1, where fn is the nth Fibonacci number. For 2, 3, 1, he had a Catalan sequence. And for pattern 3, 2, 1, he had this sequence as well, which has close links with the Catalan number as well. And in 2021, myself and Rakton Rajao shifted focus from just counting the set partitions and then decided to look at the distinct flattened partitions. And we are interested in finding or enumerating the number of such flattened partitions avoiding a given pattern, tau. And we still looked at patterns of length 3. And these were our findings. Still for 1, 2, 3 pattern, we had a trivial counting sequence. For 1, 3, 2, it was just a sequence of ones. For 2, 1, 3 and 3, 1, 2, we had a power of 2. For pattern 2, 3, 1, we had a Motzkin sequence, Motzkin numbers. And then for pattern 3, 2, 1, we had a Catalan number. So you realize that in our case here, we found that all those flattened partitions, which are 2, 1, 3 avoiding and 3, 1, 2 avoiding, still had the same counting sequence, which is a power of 2. Still under introduction, Mansour, in his book on Combinatorics of set partitions, under section 3.2, where he was looking at the different research directions, he posed an open problem about enumerating the number of set partitions of n whose flattening avoids a pattern of length 4. So this problem that Mansour posed was addressed by Liu and Zhang, who indeed investigated the number of set partitions whose flattening avoids those patterns of length 4. And inspired by Liu and Zhang's work, we decided to explore what happens if you look at the avoidance of these patterns of length 4 on the flattened partitions. And that was our main goal. And what we got so far are the following. We realized that for the pattern 1, 2, 3, 4, we still have a trivial counting sequence, which converges to 0 at some point, I think from n equaling to 1, 2, 3, 4, 5, 6, 7. For n greater or equal to 7, then the number of 1, 2, 3, 4 avoiding flattened partitions is just a sequence of zeros. And for this pattern, 1, 2, 4, 3, we had this sequence 1, 1, 2, 4, 7, 11, 16. And the time we got this, we realized that on the OEIS, that was this sequence, and not much was known about it. But currently, several results have been discovered, and new interpretations are coming for this sequence. Then for these two patterns, 1, 3, 2, 4, 1, 4, 2, 3, we had.
Sorry, Olivia. Looks like the slide has somehow stopped. Could you unshare and then share again, please?
You can't see the slides?
Yeah, it is a. I'm at the page number 4, or at the moment.
Okay.
Where are you right now? It
Wow.
hasn't
I was on
moved.
page 8. Okay, let me try to share
Let's try
again.
again. Maybe stop sharing and then share again. Looks like Zoom does something weird.
Okay, so I've stopped sharing, right?
Okay. Yeah, it's
Let
stopped,
me.
and let's share again. I don't know what's going on. Okay. I can see it now, page 7. It should be okay. Everybody, you can just say on chat. Yeah, all good. You can carry on, Olivia. Yeah. Olivia, you muted.
Okay, can you hear me now?
Now it's good. Yeah.
Can hear you.
So I was on this table for the sequences that we're able to obtain for each of the patterns of length 4. And I'd finished looking at for the 1, 2, 3, 4, it was a trivial sequence. And then 1, 2, 4, 3, we had this sequence here 1, 1, 2, 4, 7, 11, 16. And I was saying that by the time we got this on the OIS.
Olivia, I'm sorry to interrupt, because your slide stopped somewhere. Maybe you could perhaps summarize quickly what you did either in a couple of slides before.
So I first go back a bit.
Yeah, just go back a bit. Let's see.
Okay.
I think it froze at some point. So try to go back. Okay. That one we haven't seen. In fact, yeah, all of this we haven't seen.
You haven't.
Yeah, no. Yeah, you did mention, but we didn't see. Okay, so maybe summarize quickly and then we move on.
Okay.
Yeah, maybe from here. Yeah.
So let me go back. Maybe
No,
I sent
up
my
to here.
slides.
You can start from slide 6.
Slide 6.
Yes.
This one, that one that is on right now. Yeah.
This one, eh?
Yeah.
That
Okay.
one.
Sorry about these. Like my slides I've never gotten these issues. I don't know why it had to happen today. So I was saying that myself and Raptondra Jao in 2021. Okay, let me first come back here a little bit. So Catalan had done work on the avoidance of patterns of length 3 on set partitions whose flattening avoids a pattern of length 3. And in my work with Raptondra Jao, we decided to focus on the distinct flattened partitions because we've already seen that this flattening operation is not injective. So for us, we are interested in the distinct flattened partitions that avoid a pattern of length 3. And these were the results that we obtained. The most interesting ones being pattern 213 and 312, both of which had the same counting sequence, that is a power of 2. Pattern 231 had a Motzkin sequence, and then 321 gave us a Catalan sequence, Catalan numbers, and 123 was just a trivial counting sequence with only 3 ones and the rest being zeros, while pattern 132 had just a sequence of ones. So are you following?
Yes.
Yes.
Okay. Then Mansour, in his book titled Combinatorics of Set Partitions, posed some open problem under section 3.2, where he was trying to give different research directions. And the problem he proposed was the one of looking at the number of set partitions of n whose flattening avoids a pattern of length 4. So this problem was addressed by Liu and Zhang in 2015, where these two investigated the number of set partitions whose flattening avoids each of the patterns in this set, patterns of length 4. And our motivation for this study, or the results I'm presenting, are from Liu and Zhang. And for us, we now wanted to see what happens or which sequences we get if we decide to look at the avoidance of each of these patterns of length 4 on the distinct flattened partitions. And these were the sequences that we were able to obtain. So for pattern 1, 2, 3, 4, we still had a trivial sequence 1, 1, 2, 4, 5, 3, 0. And then the rest of the terms here are zeros. Then for pattern 1, 2, 4, 3, we had this sequence, which on the OEIS is this sequence here. And by the time we got it on the OEIS, there was not much that had been discovered about this sequence. And currently, when you try to check, at least there's some work that people are doing and new interpretations are coming up. Then for pattern 1324 and 1423, we had this sequence, which is a power of 2. 1342 still gave us a Motzkin sequence. And then these last 3 patterns gave us a Catalan sequence. So those were our findings. And now I want to briefly take you through the properties of flattened partitions avoiding each of these patterns of length 4. So under the 1, 2, 4, 3 avoiding flattened partitions, we realize that any permutation pi which belongs to that set of flattened partitions avoiding pattern 1, 2, 4, 3 has at most 2 runs. Because in case you suppose that you have 3 runs, say R1, R2, and R3, then there would exist some element C in the third run, for example, so that that element C is smaller than the last element in the second run. And looking at, say, the first 2 elements in the first run, the last element in the second run, and the first element in the third run, that would already form a 1, 2, 4, 3 pattern. So the maximum number of runs that this flattened partition can have is at most 2. So that was one of the properties that we got. And then the second property was that if you suppose that you have pi, which is an element from a set of 1, 2, 4, 3 avoiding flattened partitions, and supposing that pi is not an identity, then the elements 1 and 2 must belong to different runs. Otherwise, if they're in the same run, and because our runs are ordered lexicographically, that means the first entry is always 1 in each flattened partition. So if you have 1 and then 2 is in the same run, that means 2 has to follow 1. And so the last element in that run, together with the first element in the next run, that would form a 1, 2, 4, 3 pattern. So for us to avoid that, we realize that these two elements, 1 and 2, must belong to different runs. And then another interesting property that we got was that if you let R1 and R2 be non-empty subwords, such that the concatenation 1 R2 R1 gives us the identity flattened partition, then sigma written in this form 1 R1 R2 is an element in the set of 1, 2, 4, 3 avoiding flattened partitions. And from this property, we can actually, from this equation 1, we can actually observe that in each of these non-empty subwords, the elements are actually consecutive. That's why they are able to give us the identity flattened partition under this concatenation. And now, using those three properties above, we're able to come up with a combinatorial proof of this recurrence relation. So the recursion, the sequence that I showed you above, satisfies this recurrence relation subject to this initial condition, and we're able to give a combinatorial proof for this, but it was mostly relying on these three properties that I've talked about. And from that recursion, we're also able to get a generating function, and it was nice because it is closed and only depending on n. So if you don't want to use a recursion, then you can just use this closed form. So far, that's what we have under the 1, 2, 4, 3, avoiding flattened partitions. Are we on the same page, the slides?
We're good, Olivia.
Yes.
Yes.
Okay.
Yes.
Yeah.
Okay. Now, let's look at the 1, 3, 2, 4, 1, 4, 2, 3, 1, 3, 4, 2, and 1, 4, 3, 2, avoiding flattened partitions. So before I take you into what we've so far got on these, each of these, we'll call a result from my paper and Rakton Rajao, where we proved or constructed a bijection between
Olivia, sorry.
Yes.
Right after you confirm, I think it stopped again. Where are you right now? We are still in 1, 2, 4, 3. 1, 2, 4, 3 avoiding pattern. So 1, 2, 4, 3. That's theorem 3. We are.
Okay.
Where are you right now?
According to my screen, it is showing page 12.
Oh no, no. So you have to. I don't know what's going on.
I don't know. Now, maybe is
anyway.
it possible if I send my slides and then someone just helps me share them?
You can send it to me, and then if it stops again,
Yes, then you.
but then I will probably suffer the same problem as you. I'll try.
Let me send to Yvonne. Is it
Yeah,
okay?
yeah. Actually, I was going to say, send them to me. I try to share with you.
Yeah, send it to Yvonne, and then you can also unshare and then share
Yeah,
again.
I've sent to her.
Let's see how it goes.
So let me share again. Oh, this is annoying.
I don't know. I've never seen this before. So something happening in my career there. There we go. Yeah. We didn't miss much because I remember you mentioning this, but we always didn't see the slide. We're good now. But you're muted now, Olivia.
I think she's muted.
Yeah. Let me try to ask. Good.
Okay,
We're good?
so are you now on page 12?
Yes.
You can see page
Yeah.
12.
Yeah.
Yes.
So I was saying that in my work, together with Rakton Rajao, we were able to construct a bijection between 213 and 312, avoiding flattened partitions. And this bijection was interesting in a sense that besides the two sets being counted by the same sequence, it was preserving some statistics. And one was the number of runs and the length of each of the runs. So it was run preserving and was also preserving the length of each of the runs. And we are going to use this result to prove some bits in the next theorem. So in the next theorem, we are saying that let n be a positive integer, then 1, the number of 1, 3, 2, 4 avoiding flattened partitions is the same as the number of 1, 4, 2, 3 avoiding flattened partitions, and this gives us a power of 2. And in the previous work, when you're looking at patterns of length 3, that theorem I've just told you about the bijection between 213 and 312, we still had a power of 2 as the resulting counting sequence. Then 2, we have that the number of 1342 avoiding flattened partitions gives us the Motzkin sequence. And we also had a Motzkin sequence under patterns of length 3, and that was pattern 231. Then 3, the number of 1432 avoiding flattened partitions gave us a Catalan number sequence, which is the same sequence as we got for the number of 321 avoiding flattened partitions. So now I'll prove only the first one because the rest of the proofs follow analogously. They're the same. So now what we want to prove is that the number of 1324 avoiding flattened partitions is the same as the number of 213 avoiding flattened partitions. And I proved this by, first of all, supposing that we have a flattened partition pi which avoids 1324, and the goal was to show that pi also avoids pattern 213. And we did this by contradiction and supposing that pi is not 213 avoiding. And we ended up, we finally, at the end of the proof, realize that if you suppose that pi does not avoid pattern 213, then it would imply that pi also does not avoid pattern 1324, which contradicts our initial assumption that pi is an element which is 1324 avoiding. And so this tells us that all 1324 flattened partitions, 1324 avoiding flattened partitions, are actually also 213 avoiding. And conversely, we did the same by supposing that pi is a flattened partition, which is 213 avoiding, and the goal was to show that pi is also 1324 avoiding. And still, by contradiction, when we suppose that pi is not 1324 avoiding, we came to the conclusion that it would imply pi is also not 213 avoiding, which still contradicts our initial assumption that pi is 213 avoiding. And hence, we still came to the conclusion that all 213 avoiding flattened partitions actually also must avoid pattern 1324. And from these two statements, we came to the conclusion that these two sets now must be the same. They have the same cardinalities. And using the same arguments, we would do the same for pattern 312 and pattern 1423. And then we'd come to the conclusion that the number of 312 avoiding flattened partitions and the number of 1423 avoiding flattened partitions would be the same. And now when we recall our bijection between the 213 and 312 avoiding flattened partitions, then that would mean that actually all these four sets now, the 213, the 312, 1423, and the 1324, they all have the same counting sequence, and that is a power of 2. And analogously, using a similar proof of the same nature, we also proved that the number of 1342 and 231 avoiding flattened partitions would be the same. And the same applies to pattern 321 and 1432. Okay. Are we on the same page?
Yes, Olivia.
Yes, yes.
Now, so now let's try to look at additional properties of the 1432 avoiding flattened partitions. So we realize that if you have an element, which I'm calling sigma, to be a 1432 avoiding flattened partitions, then there exists an integer k greater or equal to 0 and less than or equal to n minus 2, such that that permutation of flattened partition, sigma, has this form. So for convenience, we decided to label from the right to the left. So you have the form sigma 1 up to sigma k, then sigma k plus 1 onwards, moving towards the left up to sigma, and we just decided to index from the end. So we have an integer k such that this form here satisfies 1 sigma of k plus 1 equals to n, and then the subword on the left, on the right of n, is strictly increasing because you're seeing that we are having sigma of k being less than sigma of k minus 1, being less than, and so on, up to sigma of 1. So it is strictly increasing after n. And then on the right of n, that subword, which is sigma n minus 1 up to sigma of k plus 1, is a 1432 avoiding flattened partition of length n minus k. And I'll just briefly talk about this and why it is true. It's because when you look at this form here, we've said that the subword sigma k up to sigma 1 is strictly increasing. So it would mean that if we remove that subword, if we delete it from sigma and then reorder the remaining entries, because it is strictly increasing, removing it or adding it will not affect the 1432 avoid. It will not introduce that pattern at any one point. So that's why even if we do away with it and it has k elements from sigma 1 up to sigma k, then that means if we remove it, we are remaining with a subword of length n minus k. And because its removal doesn't in any way interfere with the avoidance of pattern 1432, then that means we shall be left with a subword of length n minus k, which is still 1432 avoiding. Yeah, but the detailed proof is maybe when the manuscript comes out, you'll get a chance to look at it. And we are also able to come up with a recurrence relation for these numbers, the number of 1432 avoiding flattened partitions, and they were found to satisfy this recursion. And maybe some small hints about the proof. For the first summand, realize that if you have a flattened partition of length n minus 1, which is 1432 avoiding, then inserting n at the end of each such a flattened partition will not affect the 1432 avoidance property. So that this set alone of flattened partitions of length n minus 1 avoiding 1432 contributes this number to the set of 1432 avoiding flattened partitions of length n. And for the second term here, let me see. We are mostly focusing on the position of n and then looking at the subword either on the left or on the right of n. And using this form here, realize that all permutation sigma will have this form where we are having a concatenation of two different subwords. And those two different subwords then give us this second summand here. And yeah, I try to give an example of how this was done. But because we are time bad, I'll not go through it. So I'll end here for now. These are some of the references that we used. And thank you so much for listening.
Well, thank you very much, Olivia, for the great talk. We're welcoming questions now. So if you have a question, just speak. Just unmute your mic and speak.
Maybe Naina, I can go.
Go ahead, Yvonne.
Yeah, for me, it's not a question, but an appreciation. I know Olivia is majoring in matters to do with set partitions, and I'm always enjoying listening to her talks whenever she's giving one of them. So this is some extra results from what I previously knew that she was working on. So despite the challenge with the slides, Olivia, thank you for your presentation. It was quite good.
Thank you, Yvonne, for that comment. Actually, I also listened to when you're defending your PhD.